Okay, so if we now look at a slightly different scenario, I've got here in simulation. It's a pendulum, but it's not a pendulum with a light in an elastic, string. It's a rod. Okay, so then the rod has no weight for intents purposes, so it's a light rod, and what this means is you get a similar situation with a pendulum, but we're going to have different behaviors when we start going to the extremes. So how it's currently set up, it doesn't look much different from if it was a piece of string. So let's speed it up a little bit, or let's make it go a bit faster. And if you go a bit faster through that bottom of the cycle, it's going to go a bit further up, isn't it? Okay, so you can have a situation where it does the full turn, or it might well be, oh, I've managed to, there you go, right, let's see what it starts from there. Right, okay. It's a bit glitchy, but just I've got that pendulum working. It's going to oscillate, but it's going to, now in the scenario with the string, if I'd set this model up when it got up to that extreme moment up above, the string would lose its tension and the object would sort of fly as a projectile, sort of in and down into the middle of the circle and down below. So the rod is keeping it fixed on, effectively, you can imagine an imaginary rail, I suppose. And you can see the various different parts. You can see the weight from the gravity going vertically down, and I'm showing currently the green components of that gravity, perpendicular and normal to the line to the radial to the center. The blue line, also you got the velocity being shown as well. The velocity obviously changes, it slows down, it gets to 0, and eventually points in the other direction as it comes back down in the other direction. You can see a tension described, that red arrow that points towards the center of the circle, and you can see it sort of points in different directions. We can talk a little bit more about that in a moment. It's in terms of sort of how the object is coping with that circular motion and the way in which it's being fixed on that imaginary rail. You can also see the transfer between the kinetic energy and the potential energy in these bars at the side. So it gets that stationary point. Potential energy is maximized and the kinetic energy is 0. Likewise, when it's down at the center point down below, then the other way around, there's no potential energy and it's full kinetic energy. So just at this point in time here, you can see that the kinetic energy is maximized. Right, now let's just speed this up a little bit and let's get it doing the loop as well. Okay, and you can see that working its way around, and there is obviously a speed that will just get it to go over. Now I could probably play around and flute around with these numbers a little bit, and I could probably just get it going over. It's going to be something like 5.8, give or take. Probably still a bit too much. Anyway, so what is the speed with which you would have to go through in order to just get over that point. Now, one final thing I'd say to you is the other scenario that's very similar to this scenario in terms of setup is where you have a question where you have effectively a wire ring, and it's a wire loop, it's a circle of wire, and then on that wire is a bead or ring that sits on, effectively on that wire, and it's the ring that's the object that's speeding around. It's not connected to the center, but what it is, it's on a rail. So imagine, just take away this rod, and imagine instead this dotted line is a ring. It is a sort of a rail, a circular rail on which a little ring or a bead that's threaded through it is going around after being sent on, and let's assume there's no friction, it's smooth, etc., and you'd effectively have the same forces occurring. Okay, the forces are acting from the metal wire onto the ring or bead. Okay, in the same way that the tension is acting from the rod onto the object. So the rod is creating that force. Okay, if the rod wasn't there, if it was instead on a ring, it would be the ring. The wire would be acting on the object. Okay. And the key thing to appreciate is you don't have that scenario where the string is going to go slack. Okay, and that sort of oscillating pendulum can occur above the horizontals either side. It can go way up above. I suppose you can think of it in similar ways. If you think of if you're on a swing, okay, there is a point where you can't swing really above the axle of the swing. But if you're on some fairground ride, like the big gondola, that gondola goes right up sort of above its axle. Okay, so let's go through a question and let's talk about it a little bit in terms of what's going on. Slightly different from the scenario of the string. So we have a smooth circular wire of radius r fixed on a vertical plane. The small ring of mass m is threaded on the wire and is projected from the lowest point of the wire with the speed of u. Now, if u is equal to the square root of 2gr, find the maximum height reached by the particle. So we need to appreciate at that maximum height, we have a situation where its velocity is 0, and we're wanting to know what the height is going to be. So we can again use the idea of conservation of energy, looking at the kinetic energy and potential energy, the difference between at its lowest point and at its highest point. So the sum of the energy before is equal to the sum of the energy afterwards, i.e. the sum of the energy at the lowest point is equal to the sum of the energy at the upper point, and substituting V equals 0 for the upper point, and substituting in H is equal to 0 for the lowest point, and along with U. Now I'll put in the square root of 2gr in a moment. We end up with, let's write this out. So we've got m, now we've got 2gr over 2. Now, so that's the square of the square root of 2gr. Substitute in, and we end is equal to mgh. M cancels the either side. The 2 cancels top and bottom. The g's cancel top and bottom. And we end up with just h is equal to r. So let's just imagine what that actually means. So it's moved vertically up the distance that's equal to the radius of the wire. So if you imagine our wire, that's its center. It starts at the bottom, it's fired, and the vertical height it's going to actually move is equal to the radius. So the u equals root 2gr is for that scenario of it being coming to that sort of horizontal point, I suppose, either side, and it's just going to oscillate either side. Okay, it's going to oscillate either side if it starts off with that u at the bottom being equal to the square root of 2gr. Anything greater than that, it'll actually go above that point. It'll come up the sides here. Anything less than that, it'll just oscillate just as a sort of gentle pendulum. Next part is what is the height of the particle above the lowest point when its speed is v equals root gr. So let's just be careful here. We're just talking about the same movement, okay? And so u is still the square root of 2gr. But what we're asking is, in that movement that it goes side by side, how far up that movement, how far up the side here does it go? When at the moment when it has a speed of root gr. Okay, so whereabouts is it when it has the root of gr? It obviously gets to the point where it has a speed of 0 up here, and obviously at the other side, but how far up does it go when it's at root gr? So u equals still root 2gr. The v is going to be root gr. And we're wanting what our height is. So if we just set ourselves up again with the same equation regarding energy. So energy at the lowest point equaling the energy at the higher point. The only thing here we have h is 0 for the lower point. So we substitute 2gr instead of u squared. We end up with mgr, and the 2's cancel with the half, and I suppose I can put that in, couldn't I, if you wanted to? There you go. And then the idea is that they cancel. We've got for the gr, put in instead of v squared. Now you can see that m and g is a common factor, so we end up with r is equal to half r plus h. So it doesn't take too much to work out that h is equal to a half of the radius. So we'll scroll back down a little bit there. Sorry, what we've done is we've gone half the height up. So we've gone half the height up to that point there. I know the question doesn't ask this, but if you were asked to work out the angle, okay, with the vertical, okay, it shouldn't take you too long to work out what it is. In this instance, we've got a radius of r, the hypotenuse. Now the answer we found in this instance, the height was a half r, and if we want to work out that angle there, well, the angle is going to equal to the inverse cos of adjacent over hypotenuse. So we end up with inverse cos of a half, and this works out quite nicely to 60 degrees. Just be aware, it's just a very fairly straightforward process of trigonometry if you're asked to find the angle. Now, the last bit is when it gets really, a little bit more interesting, because now find the minimum value of u. So how fast must we fire it initially such that it will just reach the highest point on the wire? So it will just get over that the sort of on the circular track and then come back down the other side. That's the question effectively. So we need to appreciate that at that highest point, v equals 0. It's just momentarily has no velocity. It just has enough, it'll go over the other side. I suppose technically, if we have it exactly right, it will literally just stop right at the top and not go anywhere. How far has it traveled? Well, vertically, it's traveled the diameter of the circle, so 2 lots the radius. So the height reached is 2r. And lo and behold, what we're doing here, we're going to do the same process again, write out the energy equation. And if we double it to get rid of the half, if we divide by m both sides, we end up with u squared is equal to 4 lots of gr. And if I square root that answer, I get root of 4gr, and I can bring that 4 outside and it becomes 2 root gr. If I could just finish off by just spending a moment just talking about forces. So just be aware when this little ring or bead is on the wire rail, circular rail, you have the weight acting down, mg, and there are various components. So the component that is in line with the center is going to be mg cos theta, where theta is the angle to the vertical. And the reaction is similar to the tension. So the reaction is the force acted by the wire onto the bead in order for it to carry on in the circular motion. Remember that the object will go and carry on in the same direction unless there's some acceleration acted upon it. It's the centripetal force that's creating the acceleration that causes not to slow down or speed up, but to change direction. As it's turning around, going around the ring, that reaction is what is causing it to stay sort of in that circular motion. So we can talk about the sum of those forces is equal to the mass multiplied by the tangential velocity divided by r. So that's a basic structure to think of in terms of the forces acting. And realize when you have the bead or ring further up the wire, you've got the reaction towards the center, you've got the weight hanging down, mg, and so the component of the mg that is parallel to or in the direction to or from the center of the circle is going to go affecting the other direction to what we thought about beforehand. The two are in opposite directions, r and mg cos theta in opposite directions. Here they're effectively going in the same directions. So let's just write in that mg again, it's going to be mg cos theta, and that's the theta, and again it's the theta to the vertical. So we end up with the sum being equal to, if my pen would work for a moment, it's going to. Now, just be aware that if you're just wanting an expression to describe, in any scenario, go with the first one I wrote out, because all you're going to appreciate is if you're wanting to start from the absolute, for all scenarios, you think of your angle being in that direction, which is greater than 90. And the cosine of an angle between 90 and 180 is going to be negative, so it will work itself out. Subtraction, if you do a subtraction of mg cos theta, where cos theta is a negative because the theta is between 90 and 180, you're going to have effectively that plus appear. So it's just if you're looking specifically at that very specific scenario above the horizontal, then it is easier to think of it in those terms, with the horizontal, the angle to the vertical being the upper vertical. Okay, and then you're using an acute angle. But be aware, this one I've highlighted effectively works for any scenario if you're working an angle between 0 and 180 from the downward vertical. There are a couple of questions involving the idea of a ring or a bead in the exercise, questions 3 and 5. One thing I forgot to mention in my first video was I would strongly recommend actually reading the notes from page 133 to 134. There's some useful examples there, and it's well worth you reading through those examples.